Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. Now, my guest today is Steve Lombardi. Steve is VP of Product at Vexcel, and if you haven't heard of Vexcel, well, as Steve puts it, they're not exactly a household name, but you've almost certainly used their data. They're an aerial imaging company operating in around 45 countries. They capture imagery at 7.5 centimeter resolution, and not just straight down. They capture oblique imagery from multiple different directions. And that's really where this conversation starts, but it's not where it ends. Because what I really wanted to dig into with Steve was what you can actually do with all those pixels. So in this conversation, we talk about object detection and we get into vector embeddings. This is the idea of creating a kind of fingerprint for every chunk of the earth, so you can search the visible world almost like you would query a database. We talk about how you can search with text, with an image, or just by drawing an area of interest on the map. And we get into some really interesting use cases. Pulling a themed layer like a personalized risk map straight into QGIS. Personally, this was one of my favorites, and I found it absolutely fascinating, and I think you will too. So please enjoy. Steve, welcome to the podcast. I'm really looking forward to this, and without sort of building things up too much, in our pre-interview, so for the listeners, we often have this pre-interview where I meet with someone like yourself and we talk about things like, what are you doing? How are you doing that? And that gives us a structure for the actual episode. And without putting too much pressure on you, you're amazing. You're awesome. That was really fun. And I remember getting off that call and thinking, I wish we had recorded that.
Yeah, that could have been the whole interview.
That could have been the whole interview. Exactly. Anyway, I've jumped over the introduction. Steve, welcome to the podcast. You're the VP of Product at Vexcel. So let's start there. Who are you? Can you put some more words around what that actually means to be VP of Product at Vexcel? And then what is Vexcel? What do you do?
Yeah, absolutely. Thanks, Daniel. Good to be here. Well, my journey at Vexcel started about 9 years ago, and I started by leading the customer advocacy team, our customer success team, and then moved into managing our products. And that's really exciting for me because it lets me work with our customers and our salespeople, our biz dev people, gathering, their requirements and their needs and channeling that back into our products. And that's what I love doing. I've been a software engineer my whole career, and this is sort of the best place for me to land with that engineering background. And, as for what we do at Vexcel, we're, not exactly a household name, but I always tell folks, you probably use our data and imagery. So we are an aerial imaging company. We operate in about 45 countries around the world, collecting aerial imagery, very unique aerial imagery, which we'll talk more about in a moment as we get deeper into the conversation. But then we license that imagery out to a variety of industries, people who are making maps, people who are working in insurance, people who are working in utilities. Most of the maps that you will use on your phone when you're looking at what's commonly called satellite imagery is often aerial imagery. There's a real difference between that. Satellites are deep in space, looking through the atmosphere. We are flying low elevation airplanes, fixed wing aircraft, carrying our, big proprietary camera systems and sensors, gathering imagery that can be easily confused with satellite, but it's much higher resolution. And it also features 360-degree views. So these camera systems that we're flying aren't looking just straight down at the Earth, but each has 5 lenses on it. And as we're flying, and we often refer to it as the Zamboni in the sky, we're just crisscrossing the sky. All of those sensors, all of those lenses are firing about once every 3/4 of a second. So we're getting 5 images of the Earth as we move back and forth across the sky, 1 straight down and then 4 coming out at roughly 45-degree angles, north, south, east, and west. You'll hear us refer to that as our oblique imagery, oblique angled imagery. And that's really, truly amazing stuff. I'm sure I'm getting a little bit ahead, but we'll talk a lot more about that.
We certainly will. So a few questions. Now we're right in the middle of things, so we might as well just carry on with this sort of technical line of conversation. 5 lenses. What are your flight heights? What is your spatial resolution? How fast are you flying? How much area can you cover? Can you give us a sense of how big like a campaign might be for you? How much area you can cover?
Yeah, we'll typically we think of, AOIs or areas of interest that we're flying. So if we're doing a city like Dallas, Texas, it's not just the downtown center of Dallas, Texas, but it's like a 9,000, 10,000 square kilometer area around Dallas is what we would consider that urban area. So we will capture imagery at 7.5 centimeter resolution. And, to put that in perspective for people that aren't terribly familiar with satellite imagery, some satellite imagery, the common stuff is off at, 1 meter per pixel, 100 centimeter resolution. The good stuff in satellite will get down as low as 60 and 30 centimeter, and we're down at 7.5 centimeter. And what that basically means is that every pixel you see on your screen represents 7.5 centimeters of the real world, something the size of a small Post-it note. And a campaign to capture Dallas, Texas might take a couple of days. We might be there with our camera systems for a couple of days capturing that area and then moving on to the next city. And we're basically doing that systematically all year long.
Is that because it's a massive area? My guess is you need a certain amount of overlap. Maybe you need to refuel. Maybe you need to stop and process some of the data. And maybe you also want to make sure you're capturing everything at the same time. So perhaps you don't start the capture early in the morning and finish late at night. That might make it more difficult to compare images, I guess. Is that the reason why it might take 3-4 days?
All of the above, really. And you're right. Obviously, we have to fly during daylight, but even during daylight, sun angle really matters. You don't want long shadows. And that means that certain parts of the country, like if you're in the United States, certain parts of the country, you might have like a 6-hour window where the light is really good and you're not getting the long shadows. And that's the time that we're going to hit that area. Now that changes as you move north to south. There's a lot of fluctuation there. As a obvious, for instance, we wouldn't be in upstate New York in the middle of winter. First of all, it's going to be covered with snow, but the sun angle is really horrible and the light is horrible for aerial imaging.
When you said 7.5 centimeter resolution, this might be the world's dumbest question, but is that also true for the oblique images?
Yeah, it's actually a really good question. The measure of resolution in an ortho image, a straight down image, is uniform. So at 7.5 centimeters we'll normalize our imagery to 7.5 centimeters. For an oblique photo, imagine, you're looking out of your plane window and you take a picture with your phone. The things that are closer are going to be higher resolution, and the things that are further away, you're going to have lower resolution. So there's a scale there. So you can't just say, hey, for this oblique image that we captured, it's uniformly 7.5 centimeters. That it's going to fluctuate. But the nice thing in the way we capture that imagery, remember we're flying like a lawnmower in the sky, and we have a lot of overlap. So that means for every area on the ground, we are going to have the highest resolution oblique. We're going to have many images of that, like your house, the house that you're sitting in right now. When the day that we're flying over your house or your office, we're going to capture about 5 or 6 images in each orientation: north, south, east, west, and top down, in those passes that we make over your house. So about 35 to 40 images, give or take a little bit. It's going to fluctuate a little, but there's going to be a lot of overlap and a lot of images, and we're going to have the meat of your building at 7.5 centimeters from all orientations.
Wow. Okay. I understood that there would be a lot of overlap, but I didn't think it would be that extreme. That's pretty amazing. And just to be clear, when we're talking about images, are we talking about RGB? Are we talking about near infrared? What are we talking about?
In our case, both. So our sensor, the Vexcel UltraCam that we're flying, is multispectral. So we're getting the RGB and the near infrared together. The near infrared is only in the top-down view, the ortho or nadir view. The oblique views are just RGB.
What can you do with that?
Well, a lot. And I should mention, as we're capturing the imagery, the sensor that we use it's a photogrammetrically accurate camera system. So we're not just catching the pixels, we're also catching the metadata. We're capturing all of the metadata about where the camera is in space. So for each discrete image that it takes, we know where it is. We know the focal length of the lens, the pitch and the yaw of the orientation of the camera as it's looking down. with all of that data that we capture in every image, you can do really exacting photogrammetric operations. So you can do things like you're not just looking at a picture of your house, but with all of the data that we've captured, we could do accurate 3D measuring of all of the roof facets of your house. For instance, we have a lot of customers that do exactly that.
Wow. Okay. So I guess, are you using something like a technique structure from motion?
Yeah, our APIs enable exactly that. So as we capture this imagery and we process it and we publish it to our platform, then we've got our APIs and services that sit in front of that data. And they expose the images, the elevation models, and that metadata that I just talked about. And when you take all of that together, you can query our platform and say, okay, I've got this coordinate on Earth, this latitude, longitude. I want to know what imagery or what collections you have that cover that area. And our API will respond and it'll give you some JSON that says, oh, yeah, we flew over that in August of 2025, on August 3rd to be precise. And these are the images that we have available. And it'll give you the metadata for all of the images that I just mentioned. And now you can programmatically decide, well, which ones do I want to use? Which ones do I want to use for, say, 3D reconstruction or roof measuring, or running it through my computer vision models to extract objects, or whatever your use case is. All of that data is sitting there on the platform for you to use.
So that makes a lot of sense that you can do this. It sounds a lot almost like a stack API that you've got, or a stack interface that you've got in front of your images.
Mm-hmm.
Are you creating other products on top of that? So typically when I talk to companies like yourself, they're creating these baseline products as well. They're also creating digital elevation models, digital surface models. Perhaps they're extracting features, known features from the images and making them available as well as the quote unquote raw product. Is that what you do too?
Yeah, absolutely. When we started the data program about 8 years ago, we weren't yet doing AI or computer vision on the imagery and the data that we were collecting. So basically our products, when we started this data program, were the imagery and the other derivative products that we were creating that aren't AI related. So our elevation model. And to explain to folks what that is, for every pixel that we've got the RGB color of, we also know the elevation of. So we're computing that. We use a process that we internally call FODAR to everyone's kind of familiar with LiDAR, which captures the elevation of a pixel, but also the color of a pixel. We use a technique called FODAR that helps us create that elevation model from our data. So our early products were the pixels that we can see, the RGB pixels, the near infrared pixels, and then the elevation models and all of the metadata that goes with it. We evolved from there. Those were our products for about 4 years, but then we started training computer vision models to extract information out of the pixels. So things like building footprints, and are there solar panels on the roof? Is there a pool in that yard? Things that occur in roadways like crosswalks and intersections and left turn arrows and school crossing signs and things of that nature. We trained models to extract all of this information, and then we do that at scale. So now every pixel that comes through our pipeline, we run through these computer vision models, and we create a new product that we call our elements. And elements are things that are derived from the pixels. And this is often what customers are after. Increasingly, in many customers' workflows, it's the pixels are nice. Looking at the pretty picture is nice, but very often you just want to say, hey, here's a coordinate, get me all the attributes for that property or for that intersection. And that's all pre-computed and ready to go. Our computer vision models have been run. So now it's a simple database lookup. You pass us a coordinate, we'll tell you everything that we know about that property. That's sort of the evolution where the pixels are still important. Often a human wants to go and then look at those pixels to reinforce what they got from the data. But for a lot of use cases, I'll throw one out. I'm an insurance company. I have an automatic price quoting system, and someone can go to my website and put in their address, and I'm going to come up with a cost for underwriting for insuring their property. That insurance company knows a lot about the property already, but they can call out to our API and say, hey, Vexcel, what do you know about this property? Does it have a pool? Is that pool fenced in? These are all attributes that we will return. Are there solar panels on the roof? Is there a trampoline, a playground? What's the roof condition on a scale of a 1 to 5? What's the roof material? All of those attributes come back without looking at any pixels, and they can use that and bake it into their algorithm to come up with an automated price quote.
That sounds really, really cool. I also know that you are, I can't remember how many countries you active in?
About 45, just over 45. I think this year we added two, India and Mexico, and we're knee deep in collecting our imagery in both of those countries for the first time. That might take us up to 47. So something in that ballpark. It's a lot of countries.
Yeah, it's a lot of countries. There's a lot of area to cover. And also, I was thinking specifically about the Elements product, like roof condition in the US, in New Zealand, and in India. Is that difficult to come up with a universal sort of marker for that?
It's not trivial. Yeah, it's definitely something that we put a lot of thought into. So our initial models were we were using the same model everywhere, but we have now been training models in different countries and different regions, especially for roof type. Roofs in Japan are a lot different than in Phoenix. And so, yeah, we are differentiating now. And also, I will say this, a lot of the work we're doing right now under the umbrella of Vexcel Intelligence, a lot of the models that we're training and working with there, they're better at differentiating without training the model on what a roof is like in Tokyo versus Phoenix. The models that we're working with now are better at understanding those differences without us training on those differences, if that makes sense.
Yeah, it does. Could you tell me, describe for me the difference between object detection and, say, embeddings? Because I would like to go on and talk about embeddings. I know you work with this, but I think we need a definition first. Like, how are these two things different from each other?
Sure. Let's start with the object detection. And that's sort of what I've been talking about as our elements. So for object detection, we're going to look at every pixel, and we have trained models to detect certain objects. And this is a finite list of things. It's not 500 or 50,000 things. We've got about 80 elements. Like I said, there's roadway elements and there's property elements, and they're time consuming and expensive to create. We have people that do tagging. So if I want to understand solar panels on a roof, I've got to tag solar panels on a roof. And you can imagine there's so many different conditions that you're detecting them under. There's going to be some tree overhang, and there's going to be one shot was a little bit blurry because the pilot took a hard left turn or something. So your models have to be resilient to all of this. And therefore, we have about 80 objects that we recognize. Now, this year, we have introduced what we call custom elements. And with custom elements, our customers can come use our APIs or go to an interface that we provide, and they can tell us what they are looking for. So I might be looking for grain silos on a farm. I'm a health inspector for farms, and I need to find all of the grain silos in New York State. That is not an element that we have trained for, but we now have a system that does object detection and does tie in with the embeddings, which we'll talk about in a minute. But just take a leap of faith at this point and say, yes, we will help you find your grain silos in New York State using computer vision techniques through our API and return those for you, just like we would return our pre-built elements. So just like you can query and say, hey, with this coordinate, tell me the roof condition of that house. Now you can say, hey, I've got this coordinate. Tell me if there is a grain silo there. And if there is, return the exact bounding box for it. There is one key difference, Daniel. Our regular elements are pre-computed. It's part of our regular production pipeline. So they're all sitting in a database just ready to be queried. When a customer says, hey, I want to make my own elements, I need to find all of these grain silos, that recognition is done in real time. So each recognition might take a half of a second, and you're doing many of them. So you may want to go and get a cup of coffee while that is happening, and you come back and you've got your database of grain silos.
But does that mean, as the customer, I want to find, I think we talked about letterboxes last time, but let's pick something bigger. I don't know, cars, beach umbrellas. Do I need to show up with all of the data points for you to search for that element? So I want to look here across these points or these areas of interest, or will you scan the whole country? How would that work?
Great question. That leads into the embeddings. So there's two ways that you can do that. If I know where the farms are, if I already have a database of the 1,000 farms that are in New York State, I don't have to search for them. You can pass in the coordinates one by one for each of those farms, and we'll look for the silos on those farms as I just described. But now, let's say you're starting with a clean slate, and you don't know where the farms are. You need to find the farms, and then for each farm, you need to find the grain silos. This is where our vector embeddings come in. And before I explain how that works, let's talk a little about what those vector embeddings are. This is a new product for us. We're actually in preview right now. We started this in January. We're going to go to production about 2 months from now. So around the end of summer, we'll be taking this to production. And the idea is simple. We've got a model for creating vector embeddings. Think of that as a fingerprint for a chunk of Earth. And we divide the Earth up into a grid. Each grid cell is about 100 meters square. And for each of those grid cells, we're going to take the imagery that covers that grid cell, the top-down view, as well as the north, south, east, and west oblique views. We're going to give them to a special model, an embedding model. I think we were talking last time about how you can't go on, if you work in our industry, you can't go on LinkedIn right now and not read about all of these geospatial foundational models that do embedding. We're training our own right now, and we will, in about 2 months, just turn it on and embed all of our imagery. So we will have these fingerprints for each of these 100-meter cells on Earth. Once you've got that, that's your database of vector embeddings. Now I can do nearest neighbor queries into that, and I can say, hey, I am looking for farms with livestock in New York State. And we'll take that phrase, farms with livestock, we'll create an embedding for it, a fingerprint, and we will go and compare it with all of the other fingerprints that we have created, all of the other vector embeddings that we have created in New York State, and the candidates will come back. The top farms with livestock will come back. Now I've gone from, if I'm still on a mission to find all of the grain silos in New York State, I don't have to process every pixel now. I started with a clean slate, and I asked the embeddings, give it a geofence, and I say, give me all of the things that smell like farm that are in this area. And now you go from a huge problem where, if I had to process every pixel of New York State, that's a very expensive problem. If I'm grabbing my elements, I'm going to, run computer vision algorithms to extract grain silos. That's a lot of pixels to tear through. With embeddings, you go from all of New York State to the 500 farms. Now I'm taking the pixels that cover those 500 farms and giving them to that secondary model that's doing the precise object detection. And you've gone from a very expensive, long-running task to something that you can do while you're getting a cup of coffee. That's what makes vector embeddings remarkable. It's one-time processing to create those embeddings, to create the fingerprints. But once you've done that, you can search through your pixels semantically as if you were doing a SQL query to a database. It's that simple. It's really fast and elegant.
Do you think that vector embeddings will replace object detection? And if they're not going to, when should I use object detection? When is that the right tool? And when should I be thinking about embeddings?
I think they complement each other. With the embeddings, think of embeddings as getting you to an area that probably has the thing you're looking for. And if that is the end of your mission, if you only I need to find ports in the Albany area, and I don't need to identify specific things in the ports. I should tell you, I keep using the Albany example because it was one of the first cities as we were doing our preview earlier this year. It's one of the first cities that we ran through our embedding model. So I lean on Albany a lot for my examples. But if I'm looking for all the ports in Albany, I can search with my embeddings, and the results are going to be these 100-meter by 100-meter cells that probably are ports. If that's my end goal, I'm done at that point. But if I really do need to be more precise and say, where are the ships within those ports? Or where are the docks? Where are the cranes that take cargo? I don't know what those cranes are called, but we've all seen them in the ports. If I need to identify how many cranes are in that port. Now that secondary model, the object detection model, becomes critical. So it really depends on what your use case is. But both of these capabilities are exposed through our APIs. So customers get to decide, like depending on their use case, they choose how to mix and match those capabilities using our APIs.
That's really cool. That's a really, really good explanation. I appreciate that. How did you land on the 100 meters by 100 meters as a way of tiling up the world?
Very good question. It came through experimentation. And I should point out the ultimate cell, we're using those 100 meter by 100 meter cells, roughly 100 meter, I should say. They corresponded with level 18 WMTS tiles. So they're not a fixed size. They're going to vary with, as you move from north to south, they're going to vary a little bit in size. But that was initially the grid that we used. We said, hey, let's lay a grid down over the earth. Level 18 seemed to be a good compromise between resolution and context. If you go all the way down to level 21, let's say I'm looking at Yankee Stadium and I am so zoomed in that I'm down at a level 21 tile looking at center field in Yankee Stadium, that just looks like a green patch of grass. If I zoom out a little bit, maybe I see second base. I zoom out a little bit more. Now I see the stands. Level 18 showed enough context around the stadium, around the object, around the area that you're looking at, but is still represents a small enough area that we can grab the level 21 pixels that correspond to that level 18 tile. So we're using the 7.5 centimeter resolution pixels, but the grid is the level 18 grid. That was our first formula. Now that we're moving to production, we actually, through experimentation, decided level 19 is the right cookie cutter to use. So the grid that we use is going to be even tighter than the 100 meters down at level 19, but we'll still be using the level 21 pixels. So that's the formula that we landed on that gives us the best balance between context of what you're seeing in each scene, what's going to be captured in each embedding, with the resolution.
Let's say an object was completely contained within that 100 meter by 100 meter cell. But you talked about context. So if I think a particular house, a castle, let's say a castle is completely contained within that 100 meter by 100 meter, but the context of the castle, it also has some grounds attached to it. Will those neighbors of that cell, will they get extra, points? Will they show up in my search because they're providing context that they're right adjacent to that castle if I'm searching for castles?
Yes, it's actually quite elegant the way it works. And this is also thanks to the oblique imagery. Now, remember, for each of those cells, we're looking at the obliques, and the obliques are going to leak over the edges a little bit around the cell. And so the embedding model sees those pixels as well. We intentionally don't cut them sharply to that cell. We let that bleed happen naturally. So now when I do my search, one of my first searches when I was experimenting was buildings that look like a palace, keeping with your castle theme. And this was kind of cool because that's a very difficult query if you only have the top-down imagery. If I look at the capital of New York State in Albany, the building looks very much like a palace. It's a very grand building. But if you just look at the roof, it looks like a normal, mundane roof. When I do that query for buildings that look like a palace, and I query in New York State, it's the first result that comes up because that embedding model looked at the sides of the building and looked at the area, the grounds around it as well in the adjacent cells. Those cells together are all going to come back as results. Each will have a probability score. The central building is going to be the highest score, and you'll see them fall off. If you plot them as a heat map like we do in our studio application, you'll see the heat map fall off as you are moving away from that central building that appears to be a palace.
That is really, really interesting. So I never thought that oblique imagery, I always thought like, okay, more data, more better. Okay, the more data we put into this thing, the more accurate, hopefully, the fingerprinting will be. I had never sort of thought about how the oblique imagery could help add context and that bleed that you're talking about. What about the other products that you're creating? Is the digital elevation model, the digital surface model, are they embedded in this fingerprint?
Another great question that kind of looks to the future. we did some early experimentation as we were working with embeddings, and we said, if we can bring in 5 different orientations, we should be able to bring in our elevation data as well. We did some experiments early on that were promising, but we didn't quite nail the formula. So what we decided to do is come out with our first version in production where you can use those embeddings in conjunction with the elevation data, but we didn't bake the DSM, the elevation data, into the embedding. But we're working on that. We've made some nice improvements in our labs, and I'm looking forward to seeing where that goes, because then you can start asking questions like, find me buildings that look like a palace that are on a steep hill, as a for instance. That'll all be baked. The land that embedding is on will be, maybe a more practical use case would be, I'm looking to buy a new home and I want this much square footage in the backyard. I want a relatively flat parcel of land because I'm planning on putting a pool in. That's a reasonable query to ask of the embeddings once you've brought the elevation data into the mix of the multimodal embedding.
That's really interesting. And I was thinking back to your previous example around the insurance company. So, tell me something about this house. You have images of this house. What's the roof condition? That kind of thing. And I was thinking with the elevation data baked in, like, how likely is this place going to be affected by a landslide, climate change? Elevation plays a big role in that kind of thing. That would be fascinating.
Even outside of the umbrella of Vexcel Intelligence, that is a real powerful use case that our customers use today. In addition to the digital surface model, we have a digital terrain model as well. Quickly, the difference between them, think of the digital terrain model is a bare earth model. The elevation above sea level of every pixel that we're flying over, as if there were no trees, as if there were no buildings. That's the digital terrain model. The digital surface model is the one that people generally think of when they think of our elevation models. This has buildings and trees and bridges and every human-built structure as well as the naturally occurring world. Those two models together are very useful when you're doing things like flood modeling and flood risk modeling. If the sea level were to rise here, what buildings are going to be underwater if there's a foot of sea level rise, that kind of thing.
I want to sort of dive into this idea of querying the embeddings. You said before that if I'm a customer, I can show up and say, find me all the grain silos. How do they do that? Do they have like images that are showing grain silos? Do I have to bring on my own labeled data set and say, this is what it looked like? Or do I type into a box like grain silos? Or, is there some prompt engineering involved? How does it actually work?
The simplest way is to literally type into our search box grain silos, and that will work. We take that phrase, grain silos, we embed it using the embedding model. That gives us a vector that matches all of the fingerprints, all of the vectors in our database, and we can go and search that. But you can also search by image. Let's say you have a photograph of a grain silo. You can upload that to our system and say, I need to find things that are like this. And it's pretty remarkable. You upload that image, we will similarly create an embedding for it that gives us a fingerprint. And semantically, that fingerprint is in our latent space. It's in our semantic universe where grain silos live. And we take that and we give it to our database. We do a nearest neighbor search and we will get grain silos. Another cool way to search is to use the map itself. So if you're looking at something, if I'm looking at a grain silo, I can go into oblique mode. Now I'm looking at the broad side of a grain silo. I can drag a box around it and say, find me things that are like this. And we will create an embedding for that region that you just drew the box around in oblique mode. We'll go and do a nearest neighbor search for that. So there's a lot of different ways that you can trigger a search. Here's one more fun one. And I stumbled upon this early on when we first had this capability where you can take a picture of something, a photograph of something and upload it that doesn't occur in the aerial imagery, but we will extract like, what is that semantically? What's the concept of this photo? So I took a picture of Serena Williams and uploaded that playing tennis. And the model embeds that. We don't have Serena Williams in our imagery, but it looks at that photo of Serena Williams and it's extracting I see a tennis racket. I see a tennis player. I see Serena Williams. All of that gets distilled down into the embedding. And in that semantic universe, in that latent space, that coordinate, that 1200 dimensional coordinate lives where tennis lives. And so what comes back at that point is tennis courts. The results that you're going to get from our embeddings are going to be tennis courts. That's a fun example, not necessarily practical, but let's take a practical approach. What if I took a photograph of a cell tower or equipment that sits on top of an electric utility pole and I say, hey, go find me this? It works the same way. I can have a photograph of an electric utility substation taken from the ground, and I can upload that into the system and say, find me things that are like this. And it works beautifully. We take that photograph, we extract the semantic juice out of it and create that embedding, and then go back into the database and search for things that are nearby in that semantic universe. It's a really wonderful way to query.
Well, to be honest, I don't think I can truly wrap my head around what this means and what the possibilities this opens up. The idea of being able to query the visible world is pretty amazing. So maybe a better way of sort of tackling this is to think about, like, how can we make the search better? So there's been a lot of talk recently about prompt engineering. Get good at prompting. The better you are at prompting, the better the results you get back. What would make the results better? Like more images of grain silos from a lot of different angles, a detailed description of a grain silo. If you talked about drawing on a map, do I need to go to 5, 6 different locations in different areas and say, this is a grain silo, this is a grain silo? What makes the query more accurate?
Right now, we are adding some features into our application. And our application for all of these capabilities that we've been talking about, we call it Vexcel Studio. And in Studio, I can do searches with embeddings. I can draw a geofence and say, I want to constrain my queries to this area. You'll get your embeddings queries back when I search for farms with grain silos. And then I can do the object detection and extraction and export my exact location. So that's a product that we have live today. But what we're adding to it is the ability to refine those results. So with a simple thumb up and thumb down of those embeddings results, like let's say, here's a pretty practical example. I'm looking for solar farms, and I do a search for solar farms, and I'm going to get back mostly solar farms. I'm searching in New York State. I'm going to get back a lot of solar farms, but I'm also maybe misunderstood. I might get some regular solar panels on a house, and maybe I get some farm things that aren't really solar farms. So there was a little bit of confusion there. I can thumb up and thumb down about 10 results and say, yeah, these are definitely solar farms. Oh, and by the way, I'm going to put a thumb down on this house that has solar. I'm not interested in that. And this thing that is a farm, thumb down. After I do that, I hit a button and we train a classifier model at that point, like a linear probe. And that is used to refine future results. So with just 10 seconds of clicking on a few things, you can now fire another query and you will get back just the solar farms. The embeddings are still going to come back with some false positives, but using that classifier model, you're only going to see the ones that were truly solar farms. So it's that level of human in the loop. I'll call it tagging, but you're basically giving some hints to a classifier model that can help cut out some of the ambiguity.
That refining of results, will that bleed over into other sessions? You go and look for solar farms. You do some refining of results. I come later on. We're not connected. Start looking for solar farms. I refine the results. Is there any sort of network effect here that makes it better for everyone, that you increase the accuracy over time for everyone because people are tagging, labeling, confirming the results that they like or don't like?
The door is open for that, but right now, the way our system works, it's really private to you. We don't do any data sharing, so your session is private to you. You can save your results. Like, let's say I work in the solar field, and I'm going to be doing this analysis in Albany, but I'm also going to be doing it in Louisville, Kentucky. Once I've done my tagging, my labeling of those results in Albany, I've got that model, that classifier model trained. When I go and do my work in Louisville, Kentucky, for me, I will get those improved results. So the time that I spent doing that hand labeling, the thumb up and thumb down of some results, improves my queries it doesn't improve your queries. And that's by design. Right now, our customers, they want it that way. They are investing their time to create these classifier models. They want it to be private to them. But where you're heading is a good way to be thinking about this. You could imagine we have a more open public facing system where anyone can label solar farms. And now you've got the best solar farm detector in the world. So yes, it's definitely a possibility.
Phew, man, we have come a long way in the discussion so far. And I wonder here towards the end if it's not a good idea to sort of come up for a breath of air and look up in the helicopter, if you will, and so look down on this. There's a lot of push to collect a lot of imagery now. Do you foresee a time where we've got enough, where we've saturated the market, where we don't need any more imagery?
No. Our customers tell us no. They always want more frequent collection. They want more countries added. So yeah, I don't see the amount of imaging of the globe that is happening right now decreasing. I think there's just more and more demand. That holds true for us. It holds true for the satellite companies. It's trending in that direction. I think what's going to happen, we're going to find more and more use cases, better and better tools to leverage all of those pixels. Here's an observation. When you think of the Vexcel data program, we've been operating now for about 9 years, and we have trillions of pixels. It's an unreal number of pixels that we've collected. Many of them go unviewed. They're in obscure parts of the world. No one's going to look at all those pixels. Once you've embedded them, they now become searchable. And the impact that those pixels have will be multiplied tenfold, 100-fold. So unlocking the value of the imagery is what we're doing with Vexcel Intelligence. And this is what's happening in the industry. It's not unique to us. I think what is unique to us is the perspective that we bring, the oblique imagery, the angled imagery, the digital surface models all being wedded together. I think that makes Vexcel unique. But the trend that's happening in the industry is very broad. Anyone who is collecting aerial imagery right now, whether it's through a satellite or through a drone or through fixed wing aircraft, is looking to make it semantically searchable.
I was just thinking about that. So obviously you've been capturing imagery for a long time. You've got all of these pixels. You're creating embeddings for each pixel. Is time part of that embedding?
Yeah, absolutely. So you've got vintages of imagery, and that means you have vintages of embeddings, and that means you can compare them across time. So I'll focus for this example on Austin, Texas, a city well known for the amount of change that it has gone through and is still going through over this current decade. We've embedded early on as a test city. We embedded multiple generations of the imagery that we have over Austin. And now we can ask questions like, find me areas of incredible change, a lot of change, and then classify those areas for me. And this is, you're kind of getting here into an agentic outcome where I'm using the embeddings to very quickly find the areas of change, but now I'm using an agentic model to do the classification. So I can look at all of Austin and say, highlight the areas of change. And you'll see that light up on the map. There's a big change here, a heat map. You're going to have a lot of red here, a lot of green here where there wasn't a lot of change. Now you say to the agentic model, go and classify each of those. You just found 50 areas of change. Are they due to natural land erosion, residential construction, commercial construction, tree clearing? What's the reason for the change? And you'll now get that answer. So you've gone from a ridiculously hard problem to something that you can answer in 30 seconds.
Yeah, that sounds wild, to be perfectly honest.
Daniel, can I throw out something new? I think this will resonate with you and your audience. This is something that we've done recently and we're productizing, but I think it fits into what you just asked about. You think about going to a tool like QGIS and you've got a base map there. You can pull in a layer of Vexcel imagery as a base map, an ortho image, tiled image. What we're doing now is exposing vector tile services based on our embeddings. And the way you add that layer in QGIS is by specifying some concepts. So let's say I work in real estate and let's get away from real estate because that's such a common, people think about imagery in real estate a lot. Let's say utilities. And what I'm looking for, I want a heat map of where electric utility infrastructure is. So when I think about how I can query that with our embeddings, let's say I was searching for solar farms, high tension power line towers, high tension power lines themselves, electric utility substations, wind farms might be another one. Each of these is a component, a concept related to electric utility infrastructure. If I take all of those concepts together, I can make a really incredible heat map across Austin or Albany or wherever my map view in QGIS happens to be. And so imagine a tile service that takes those concepts as input when you're in QGIS and you right click on your XYZ services and you say, hey, I'm going to add a new service. On our service now, we have some parameters that let you specify those concepts, and you can weight those concepts and say, solar farms are really important to me. That's zero point 0.9 on a 0 to 1 scale. And those electric utility substations, they're 0.8, et cetera. I've got my 4 concepts. When you visualize that layer, it's a heat map that matches your concept. It's a personalized heat map, a personalized base map for you to do your work on in QGIS or in ArcMap or whatever tool you happen to be using. You're leveraging those embeddings, and you're not looking at the pixels because you don't care about the pixels. There's no way the human brain can look at all those pixels and know where are the hot spots for electric utility infrastructure, but we'll give you a clean heat map that matches your exact concept. This is a super powerful way for people who work in GIS to take advantage of our vector embeddings without having to know what that means. They're just saying, these are the concepts I'm interested in. Give me that base map. And then imagine being able to overlay your infrastructure on top of that base map. And the backdrop isn't aerial imagery. It's your concept that you just brought to life. It's incredibly powerful. This is a new product for us that we'll be bringing out at the end of summer when our embeddings are going from preview into production.
Wow, honestly, man, that's really, really, really interesting. I love the way. So before you talked about studio, I think, but studio always means you're going to somewhere else and doing work somewhere else. There's nothing wrong with that, but more like people would like to stay in their own environment. So
Right.
The idea of making this available through a tile server is, in my mind, really, really, it's brilliant. It's really clever, and there's going to be some fascinating use cases for that. There's no doubt in my mind.
Yeah, and I think we're going for the best of both worlds here, where if you're working in QGIS, we want you to be able to do this visualization in QGIS. That's why we've had our imagery pumped into coming out through tile services for years. So of course you could look at Vexcel base maps and do your work over the top. But when I say best of both worlds, now you're going to get this semantic base map, but you could also go into our studio and say, oh, and by the way, for this area that I'm analyzing, I do need to mine out of the pixels where all of those electric utility substations are. I need the precise location of each of them. I need a mask over each of them. I can export that out of Studio as GeoJSON and then bring that into my GIS of choice as well to overlay over that base map.
It's really cool. I'm thinking too, like of risk maps, for example. You could define what risk is for you. That heat map of risk would be pretty fascinating, especially if you can change it over time. Like, how is the risk? I don't know if you can pull in many layers, but like see how it changes over time. That would be amazing.
Yeah, absolutely. So a risk map is a really good use case for that concept map that we were just talking about. You have to define risk. What is risk for you? Is it a garbage dump that is nearby? You're in real estate. You don't want to be looking at houses that are within half a kilometer of a toxic dump. Oh, okay. Then that's part of the risk for you. You also don't want to be near that electric utility substation or the high tension power lines. Maybe you don't want to be near an open body of water like a pond or a lake in the neighborhood. All of those things are what you define risk as. We'll give you the color-coded heat map that matches that.
That is really, really cool. We talked a little bit about your sensors before. What are they going to look like in the future? Do you imagine a company like yours, will you stick with the RGB and near infrared? Could you imagine moving in like more data streams? Are we close to the 1 centimeter pixel? What do you imagine the future might look like in terms of sensors and capture of imagery?
Yeah, our sensors are really the backbone of what we do at Vexcel. And, I keep talking about Vexcel as the Vexcel data program is this 9-year-old entity. Vexcel Imaging, the camera company, was founded about 33 years ago in Graz, Austria. The camera systems are evolving. We have versions of our camera systems just like we have versions of software. So we're on the Osprey 4.2 and we're working on the Osprey 4.3 camera. The resolution gets better, the imaging gets better, the motion blur gets better. All of these things are improving. So yeah, I think we're heading towards, our standard right now is 7.5 centimeter, but we have camera systems now, new lens systems that'll take us much deeper than that. So we'll see those improvements. I don't think there's a limit there to where we will take things. And that's important for us because, as I said, it's the backbone of what we do. We're no better than the sensor. What sets Vexcel apart is that photogrammetrically accurate sensor that lets us create very exacting digital surface models. It lets our customers downstream do very accurate object detection and other photogrammetric operations. It's all about the camera system. It's really our differentiator.
What are customers asking for today? They're asking for something, right? It sounds like you're doing a lot of really interesting work, but there are definitely customers that say, oh, can you do this? Where can we go next? What about this thing here? What do you see out there? Like, what are people wanting that is on the roadmap for you?
Yeah, if you're asking there about the cameras specifically, it is about resolution. They're always asking us for more resolution, but I suspect you're asking, hey, what are customers looking for just outside of that? What do they want to do with the imagery? Here is where it does go into what people want to do with AI and the embeddings. People want answers from the pixels. Our customers have made that clear for years. We have customers that come to us. We talked earlier about our elements and how we have trained models for 40 to 80 things that we know our customers have said are important. But we get requests all the time for things that we're not going to train those models for. Providing the tools that let our customers mine that information out of our pixels is the most important thing that we could do right now at Vexcel. And that's why we've taken this focus early on with AI to create embeddings and do object detection so that customers can define what they want to pull out of the imagery. An example, one of our customers that works in commercial insurance wants to find cooking vents on roofs. Cooking vent is that mushroom vent that you see. And there's a strong risk there. If a building like a strip mall has one of those cooking vents on the roof, there's a commercial kitchen in there, potential for grease fire. We're not going to train that model. It's just too obscure. It's gold for them, but it's just too niche for us to go and train models for all these things. Now we have the tools that let our customers decide what they're looking for. What do I need to find in the imagery? And that's where we're heading. And I think that's, for the next year, we're just going to double down in that area and make sure we've got the best tools for people to find what they want to find in the imagery, find the patterns that they are looking for in our pixels.
Yeah, I think this the idea of embeddings or the technique of embedding, like creating these fingerprints that we're talking about, I just cannot see that going away anytime soon.
No.
We touched briefly on the idea of these foundational models. Made with clay is one that I think the listeners should check out. This is one based on satellite imagery for the world. And I just can't see it going anywhere anytime soon. Just because of that reason, like no one is going to train that model to look for the mushroom, the vents. No one's going to do that. But it doesn't mean it's not important. And embeddings can make that stuff happen. It can make it possible.
And make it financially viable. That's the other thing. Like any of our customers could go and train that model to find those mushroom vents, but then they got to run every pixel through there. And that's expensive. With embeddings now, well, two things. I can find the strip malls that probably have those, for one. But if you bring to us your database of strip malls, now we can do the object detection for those mushroom vents, just constrained to the geographic area, the list of areas that you bring to the table. So that works out really well for everybody as well. You're not cranking the GPUs at that point. You're not running every pixel through the GPUs to do that identification. Your embeddings whittled away 90% of the Earth, and you're down to a real small number of pixels that you have to process.
Yeah, again, I think it's fascinating. I think probably now's a really good time to wrap up the conversation. And I want to say thanks. I appreciate you slowly but surely walking me through some of these concepts. I think it's super important for people to hear this from many different angles. Like I say, a lot of these technologies are going nowhere. We're only going to be concentrating on them more. And it's really important for people to understand how they work and the use cases of them. And you did a brilliant job of that. So thank you very much.
Yeah, thanks for the opportunity. It was a great conversation, Daniel. I appreciate the invitation to come talk to you today. And I'm glad to hear that you found it as exciting as I did.
No, honestly, I found it fascinating. This idea of, searching with text, with image by selecting an area on a map alone, that idea is fascinating. The idea of pulling in a themed layer of, let's say, risk into QGIS, I think fascinating. It's really interesting stuff. And I appreciate your time. Thank you.